Have you ever stopped to think about what's actually happening chemically inside your morning cup of tea? Well, today we're going to go way beyond just brewing. We're on a mission to uncover the hidden science and pull pure caffeine right out of simple tea leaves.
So, here's the mission. We're about to go on a full-on chemical journey. The goal? To take this complex natural thing, a tea leaf, and pull out one single specific molecule, caffeine. And not just any caffeine, but pure crystalline caffeine. It's kind of like finding a needle in a haystack, but on a microscopic level. And our tool is chemistry.
Let's frame this up. Think of it like a chemical detective story, or maybe even a heist. We've got our target, caffeine, but it's locked away inside this key leaf with a bunch of other compounds, so just grabbing it isn't an option. We need a really clever, multi-step plan to get it out.
All right, so before any good heist, you've got to know who you're dealing with, right? We need to know what we're up against. So what else is actually in that tea leaf hanging out with our caffeine? Let's profile the main suspects we'll have to handle. Okay, so here are the main players in our little drama. First up, you've got cellulose. This is just the tough, fibrous stuff that makes the leaf a leaf. It doesn't dissolve in water, so that's easy. We can just filter it out later, no problem. But then we have the tannins. These guys give tea that bitter taste. And here's our big challenge. They're also soluble in water, just like our target, caffeine. That's the real puzzle we have to solve.
Now, what's really interesting here is that our target, caffeine, isn't just flying solo. It's actually part of this much larger and frankly very potent chemical family known as alkaloids. And this family has some incredibly famous and infamous members.
So what exactly are alkaloids? Well, they're these powerful nitrogen-based compounds that plants make, a lot of times as a defense. They're usually bitter and they tend to have really strong effects on us humans. And when you look at the other examples here, nicotine, morphine, cocaine, you realize, wow, caffeine is in some pretty intense company.
So every good heist needs a solid plan. And ours is all about exploiting the different properties of these compounds. We're going to use things like solubility to our advantage, peeling away the other molecules one by one until only our target, caffeine, is left standing.
Our very first step is something we've all probably done 1,000 times. We're going to brew the tea. We're using hot water as our first solvent. But, and this is important, why specifically hot water? It's not just to make it taste good, it's a critical chemical decision. It all comes down to solubility.
And this chart just shows you how ridiculously important that heat is. Look at this. At room temp, you can get about 22 milligrams of caffeine to dissolve in a milliliter of water. But get that water boiling, that number just skyrockets to 670 milligrams. It's over 30 times more soluble. So yeah, using hot water is a total game changer for getting that caffeine out of the leaves.
Okay, but here's the catch. Hot water is an amazing solvent, but it's not picky. It pulls out our target caffeine, for sure, but it also pulls out those pesky tannins right along with it. So now they're both swimming around in our tea. How in the world do we split them up?
And this is where the really clever chemistry kicks in. We're going to add a simple base, sodium carbonate. You can think of this as our secret weapon. It's the ingredient that's going to let us trap the tannins so the caffeine can make a clean getaway.
So here's how the trap works. The sodium carbonate reacts with the tannins and turns them into something new, tannin salts. And this is the absolute key move. Because while the original tannins would have dissolved in the next solvent we plan to use, these new tannin salts will not. They are now stuck, trapped in the water, leaving our caffeine totally free for the taking. It's the perfect setup.
Okay, with the tannins successfully trapped, it's time to bring in our next player, ethyl acetate. This solvent is our caffeine magnet. It's got two really important jobs. One, it doesn't mix with water at all, and two, caffeine just loves it. It's way more soluble in ethyl acetate than it is in water. So it's going to pull that caffeine right out of the tea.
All right, so that's the whole theory. That's our blueprint for the heist. Now, let's see how this all comes together when we actually put the plan into action.
You know, you can really boil the whole process down to these 4 main steps. First, we brew the tea with the base to get our caffeine out and trap the tannins. Second, we filter out all that solid leaf gunk, the cellulose. Third, we add our ethyl acetate to pull the caffeine over. And finally, step 4, we just evaporate that ethyl acetate, and what's left behind should be our pure caffeine.
Now for that all-important third step, getting the caffeine-rich ethyl acetate away from the water. Chemists use a special piece of gear. It's called a separatory funnel, and it's designed for exactly this kind of job.
So what happens inside the funnel is pretty cool. Because ethyl acetate and water don't mix, they form these two perfect, distinct layers, kind of like oil and vinegar. The ethyl acetate is less dense, so it floats on top, and that's where our caffeine is. The water layer, with all those trapped tannin salts, is on the bottom. So we just open the little valve, drain out the bottom layer, and throw it away. What's left on top is our prize.
So we evaporate the solvent and we're left with this white powder. It looks like caffeine, right? But in science, looks like just doesn't cut it. We need proof. How can we be absolutely sure that what we have is actually pure caffeine? Well, we need one final test.
So chemists have this classic, super reliable way to confirm both what a substance is and how pure it is. It all comes down to a physical property called the melting point.
And for pure caffeine, this is the magic number we're looking for, 238 degrees Celsius. That's our bullseye. If our sample is the real deal and it's pure, it should melt precisely at this temperature.
Honestly, you can think of a melting point as a molecule's unique fingerprint. Just like every person has a different fingerprint, every pure crystalline compound has its own sharp characteristic temperature where it turns from a solid to a liquid.
But here's the really neat part. It's not just about hitting 238 on the dot. It's about how it melts. See, impurities mess up the nice, neat crystal structure of a solid. This makes it melt at a lower temperature and over a much wider range. So a sharp, clean melt right around 238 degrees, bingo, we've got pure stuff. But if it starts melting way lower and kind of turns to mush over a wide range, that means we still have some gunk in there. Our heist wasn't quite perfect.
So let's zoom out for a second. What's the big picture from our chemical heist? Well, for one, it shows that chemistry is basically about solving puzzles, how to separate mixtures. We saw that solubility is an incredibly powerful tool we can control. And we even learned you can chemically change a molecule, like we did with the tannins, just to make it easier to get rid of. And finally, we used physical properties like a melting point to prove we actually succeeded.
You know, we just went through all this effort to pull out one single, very common molecule. But think about it. This exact same logic, using solvents and reactions and physical properties to isolate things from nature, it's the absolute foundation of discovering new medicines and new materials. It really makes you wonder what other incredible molecules are still locked away in plants, just waiting for the next chemical heist to bring them to light.